In this video, we're going to learn how to solve our systems of linear equations using a new technique with matrices. So a matrix is just a rectangular array of numbers. And we're going to learn how to solve these systems using these arrays of numbers, which essentially is still the same thing as elimination, but you're not going to have variables floating around everywhere. So sometimes it makes it a little easier to organize your thoughts. So let's just start right away with the description of what we're going to do. So a system of linear equations can be represented as what's called an augmented matrix. By writing the coefficients of the terms in the matrix. And I'm going to give us an example showing a system written out as a system of equations and also translated into a matrix so that you know exactly what I'm talking about when I say this. So just for an example of how you can write these, here's a system of equations. 3x plus 2y equals 5, x minus y plus 3z equals 1, and 2x plus y plus z equals 4. And I can write this as a matrix, so just a rectangle filled with numbers, by taking the coefficients in each equation and filling in the row. So my first equation, my x had a coefficient of 3, my y had a coefficient of 2, my z has a 0, and my constant on the other side is a 5. So we put a vertical line right here to represent where the equals is, and so the right-hand side goes over on that side. I have my next equation, my coefficient of x is 1, for y I have negative 1, for z I have 3, and my constant is 1. And then my last equation, my x coefficient is 2, for y I have 1, z I have 1, and the other side of the equal sign is 4. So this array of numbers here, this matrix, represents the same thing as that system of equations above it. Now, we're going to learn different things we're allowed to do with our matrix without changing our system of equations. And then we're going to use those techniques to solve using a matrix. So we need to learn what are called elementary row operations for matrices. The first elementary row operation is interchanging two rows. So, for example, if I have the matrix 1, 2, 3, 0, 4, 8, I can change it into a new matrix with this notation here. Row 1 with a double-sided arrow, row 2 means I'm going to swap those two rows. So I put row 2 up on the top, and row 1 is now on the bottom. So that's one of our elementary row operations. You can swap any two rows, and it's still going to represent the same system of equations. Learn our next elementary row operation. you can multiply a row by a non-zero constant. So if I take my same matrix from before, 1, 2, 3, 0, 4, 8, and let's say I'm going to do this row operation to it. 2 times row 1 and store that information in row 1. I know it's kind of confusing notation, but what it's saying is multiply your row 1 by 2 and take that new information and put it in row 1 in your new matrix. So I get to multiply all of my values in row 1 by 2. 1 times 2 is 2, 2 times 2 is 4, and 3 times 2 is 6. And I didn't do anything to row 2, so it's still the same. So this is another elementary row operation, and that means if I do this, that matrix still represents the same system of equations. And it makes sense when you think about it, because remember, we were allowed to multiply our equations by a non-zero constant, and this is the same thing. We're multiplying a row by a non-zero constant. Our last elementary row operation is the most complicated one. We can add a non-zero multiple of one row to another row. So for example, if I take that same original matrix, 1, 2, 3, 0, 4, 8, and I'm going to apply this operation to it, row 1 plus 2 row 2, and store that information in row 1. This says I'm going to multiply row 2 by 2 and add that to row 1. And then I'm going to write that information down in the row 1 spot. So 2 times this 0 is 0. Add it to my 1 and I get 1. 2 times 4 is 8. Add it to 2 to get 10. And 2 times 8 is 16. Add it to 3 to get 19. And then my row 2 does not change. The only one that changes by this operation is row 1. So this is the same sort of thing as adding our equations together, adding a multiple of one equation to another equation. It does not change the answer to the system of equations. Definition. A matrix is in row echelon form if these three things are true. 1, any rows consisting of all zeros. Are at the bottom of the matrix. 2, the first non-zero entry of any row is a 1, and we call this the leading 1. And property 3, the leading 1 in each row is to the right of the leading one in the row above it. So that's what it is to be in row echelon form. All 0 rows are at the bottom. The first non-zero entry of any row is 1, and as you go further and further down the rows, the ones go further and further to the right. That's row echelon form. And then we also have a reduced row echelon form. So a matrix is in reduced row echelon form. If this fourth property is also true. Each row with a leading 1 has zeros above the leading 1. So you're in reduced row echelon form if all 4 of the properties apply, and you're just in row echelon form if the first 3 apply. So I'm going to write down a couple of examples of matrices in both of these forms so that you can see what I mean by these descriptions. So row echelon form, which I'm going to abbreviate REF. Here's a couple matrices in row echelon form. 1, 5, 3, 0, 1, 6. So if we take a look at this matrix here, there aren't any rows with all zeros, so we don't have to worry about that property. The first non-zero entry in both rows is 1, and the leading 1 in each row is strictly to the right of the leading 1 in the row before it. So notice how our leading 1s keep moving to the right. So this is in row echelon form. Another one in row echelon form is 1, 4.1, 1.2, 3.1, 0, 1, 0.6, 4.7, and 0, 0, 0, 0. So this guy is in row echelon form because we have a row of all zeros, but it's on the bottom. My first non-zero entry of each row is a 1, and they're moving to the right as I go down my matrix. So those are both in row echelon form, but they're not in reduced row echelon form. If they were in reduced row echelon form, then I would have to have zeros above all of my leading 1s. So some examples in reduced row echelon form, which I'm going to abbreviate with RREF. Here's an example in reduced row echelon form. I don't have any rows that have all zeros. My leading entry of each row is a 1. They move further to the right as I move down, and above all of my leading 1s, I have a 0. A bigger example, 1, 0, 2, 25, 0, 1, -3, -4, and 0, 0, 0, 0. So this matrix is in reduced row echelon form because the 0 row is on the bottom. All of my rows that have non-zero entries start with a 1. The 1s move further to the right, the further down I go in my matrix, and above every single leading 1, I have zeros. Now, why do we care about these different forms? Well, because when we solve systems of equations using matrices, we need to use our row operations to turn the matrix into one of these forms. So we're going to first learn how to solve with what's called Gaussian elimination. First, write your augmented matrix for the system. Then, use your elementary row operations to turn the matrix into row echelon form. Then, back substitute to solve the system. So you're going to take your system of equations, translate it to a matrix, use row operations to put it in this row echelon form, and then translate it back into equations so that you can back substitute. Let's do an example of that. So let's solve 2x plus 7y plus z equals 14, x plus 3y minus z equals 2, and x plus 7y plus 12z equals 45. So the first thing that we want to do is write this as a matrix. To do that, you just fill in the coefficients. I have 2, 7, 1, 14. And then I have 1, 3, negative 1, 2, 1, 7, 12, and 45. And now we take a look at this. Is it in row echelon form right now? No, it's definitely not. The first sign that it's not is that the first entry in this first row is a 2, and it would need to be a 1. So we have to decide how we're going to make it into a 1 using our row operations. We could multiply the first equation by 1/2. I personally would not. If you multiply the first equation by 1/2, you're going to introduce fractions in here, and messing around with fractions inside the matrices, while you can do it, you should try to avoid it if you can, just to make your life easier. I personally would do a swapping of some of our rows. Remember, our first elementary row operation is interchanging rows. So I'm just going to swap rows 1 and 2. So if I do the row operation, row 1 and row 2 switch places, I will get 1, 3, negative 1, 2 for my first row, 2, 7, 1, 14, and 1, 7, 12, 45. So now I have a 1 in that leading 1 spot, but we're still not in row echelon form. In order for this to be in row echelon form, I need zeros to be beneath this 1. So let's try to get this 2 to turn into a 0. We can't just multiply the row by 0, unfortunately. That would be really easy, but it would get rid of the whole row. What we can do, though, is multiply row 1 by 2, and then subtract that result from row 2. So the row operation that I suggest we try to do is row 2 minus 2 row 1 and store it in row 2. So let me rewrite where we were. I suggest that we use the row operation, row 2 minus 2 row 1, store it in row 2. So let's take a look at what happens when we do this row operation. The first thing I want to point out is the only row that's going to be different is row 2. Our row 1 and our row 3 are not going to change. So I'm going to go ahead and fill them in just so I don't have to worry about them anymore. But my row 2 is now going to be my previous row 2 value minus 2 times my row 1 value. Well, 2 times 1 is 2, and 2 minus 2 is 0. For this guy, I'm going to have my 7 minus 2 times 3. So that's 1. And then I have 1 minus 2 times negative 1, which is 3. 14 minus 2 times 2 is 10. So that's what I get when I apply that row operation. Now notice though, I still am not done because I still have this guy that needs to be a 0 underneath my leading 1. So how can I turn this guy into a 0? Well, I can do something very similar. My row 3, I can subtract row 1 and store that in row 3, because 1 minus 1 will get me a 0 down here. So let's try that row operation. Notice in that row operation, the only row that's changing is row 3. So again, I can fill in my row 1 and my row 2 because I know they're not changing with this operation. Now to do the last row. Row 3 minus row 1. 1 minus 1 is 0. 7 minus 3 is 4. 12 minus negative 1 is 13. And 45 minus 2 is 43. So this is my newest version of this system of equations. Is it in row echelon form yet? No, but we're getting close. So I have this leading 1 with zeros beneath it. My next row has a leading 1, which is strictly to the right, so that's good. But I need to have a 0 beneath it. So how do I change this 4 into a 0? Well, we're going to do something very similar to what we've been doing. I'm going to take row 3 and subtract 4 row 2 and store that in row 3. Doing this row operation is only going to change row 3. So I'm going to fill in rows 1 and 2. And now for row 3, I have 0 minus 4 times 0. 4 minus 4 times 1. 13 minus 4 times 3, well, that's 1. And 43 minus 4 times 10, that's 3. So now take a look at our matrix. Is it in row echelon form? I have a leading 1 in each row, and each row the leading 1 moves further and further to the right. So this is in row echelon form. That means we're ready to translate it back into a system of equations and then back substitute to solve. So I have my row echelon form of the matrix, and now let's translate it back into a system of equations. I have, from my first row, 1x plus 3y minus 1z equals 2. Then I have 1y plus 3z equals 10. And I have 1z equals 3. Well, see, this is very nice now. z equals 3. I can take that and plug it into the equation above to figure out y, and then take both of those and plug it into the top equation to figure out x. So z is 3, and that means that y plus 3 times 3 is 10. So y is 1. And then taking the very, very top equation, I get x plus 3 times my y minus my z equals 2. And that gives me x is 2. So the solution to that system of equations was 2, 1, 3. And that is the same answer that you would get if you solved the system using the techniques we learned in the last video. This just gives you a different option. So what we just did was solve a system using Gaussian elimination. Now, I personally prefer what we're going to do next, which is Gauss-Jordan elimination. It's really not that much different. The only difference is instead of putting it into row echelon form, you put it into reduced row echelon form. So Gauss-Jordan elimination. It's the same as Gaussian elimination. But with reduced row echelon form. So that means you're going to keep doing row operations until you have zeros above and below every single leading one. So let's do an example of that. I have x minus 2y equals -1. 4x minus 7y equals 1. The first thing we need to do is translate it to a matrix. I have 1, -2, -1, and 4, -7, 1. So there's my augmented matrix. Now I need to do row operations to put it into reduced row echelon form. So let's start. Do I have a leading one in the correct place for the first row? I do. Do I have zeros above and below that one? No. I need to turn this guy into a 0. How do I do that? Well, I would use the row operation row 2 minus 4 row 1 and store that in row 2. So let's see what happens when we do that row operation. Again, the only row that's changing is row 2. So I can go ahead and fill my row 1 back in. And now my row 2, I get 4 minus 4 times 1. That's 0. -7 minus 4 times -2 is 1. And 1 minus 4 times -1 is 5. Now, is this in reduced row echelon form? No, it's not. It is in row echelon form. So if I were to just use Gaussian elimination, I could just rewrite this as a system and back substitute. But I'm going to go ahead and put it all the way into reduced row echelon form using this other Gauss-Jordan elimination. So why is this not in reduced row echelon form right now? Because this leading one does not have a 0 above it. So this -2 needs to become a 0. That means that I can take my row 1 and add 2 times my row 2, store that back in row 1, and that should turn this into a 0. Because -2 plus 2 times 1 will get me 0. So when I rewrite my matrix, my row 2 does not change. My row 1, I get 1 plus 2 times 0, that's 1. Negative 2 plus 2 times 1 is 0. And negative 1 plus 2 times 5 is 9. Now this is in reduced row echelon form. And so if I translate it back to a system of equations, I get x equals 9, y equals 5, and it's already solved for me. I don't have to do any other back substituting, it's just done. So I get 9, 5 as the solution to that system. And again, that's the same solution you would have gotten just solving the system using elimination or substitution. If you find that you really don't like a certain method, don't use it. Use the method that works for you. All right. I have just one last example for us because these problems take a while to go through. So last example, we are going to solve the system 2x plus 7y plus 11z equals 11. X plus 2y plus 8z equals 14. And x plus 3y plus 6z equals 8. So the first thing we need to do, put it in a matrix. 2, 7, 11, 11, 1, 2, 8, 14, and 1, 3, 6, 8. We want to use, I'm going to use Gauss-Jordan elimination again, so putting it all the way in reduced row echelon form. The first thing I want is a 1 in this upper corner. I could just multiply by 1/2, but I don't want to deal with 7 halves and 11 halves in my problem. So instead, I'm just going to swap 2 rows. I'm going to swap row 1 and row 2. So interchange row 1 and row 2, and we'll get a new version of this matrix. We get 1, 2, 8, 14, 2, 7, 11, 11, and 1, 3, 6, 8. Now, is that in reduced row echelon form? No, it's definitely not. The first thing I have to deal with now is I need to have zeros underneath that 1. So I need to change both row 2 and row 3. And we can do that 1 row at a time, but I'm going to go ahead and do them both at once to show you that you can do more than 1 row operation in 1 step, just to save you some paper. So my row 2, I need to subtract 2 of my row 1s. And store that in row 2. And then my row 3, I can make that into a 0 by just subtracting 1 of my row 1s. So this time I have 2 of my rows changing. The only row that's not changing is row 1. So I'm going to go ahead and fill that row in. Now my row 2 is going to be row 2 minus 2 row 1. 2 minus 2 times 1 is 0. 7 minus 2 times 2 is 3. 11 minus 2 times 8 is negative 5. And 11 minus 2 times 14 is negative 17. Now we're ready for row 3. Row 3 is going to be row 3 minus row 1. 1 minus 1 is 0. 3 minus 2 is 1. 6 minus 8 is -2. And 8 minus 14 is -6. All right, are we in reduced row echelon form now? No, we're still not, but at least this part's looking pretty good. The next thing we need is we need a 1 in this next spot in my row 2. And I have choices. I can multiply this middle row by 1/3. Please don't do that. Then you're dealing with 17/3 and things in the problem. That would be crazy. Instead, I can just swap row 2 and row 3. So let's interchange row 2 and row 3. If I do that, then my row 1 is still 1, 2, 8, 14. My row 2 will now be 0, 1, -2, -6. And my row 3 is now 0, 3, -5, -17. So this still is not reduced row echelon form, but now I have my leading 1 where it needs to be. To put this into reduced row echelon form, I need zeros above and below every single leading 1. So this 2 needs to become a 0, and that 3 needs to become a 0. We're going to do 2 operations again. To take care of this row 1, I can subtract 2 times my row 2. So row 1 minus 2 row 2, and store that in row 1. To get rid of my 3 down here, my row 3, I can subtract 3 row 2. So when I do those 2 operations, my middle row is not going to change. But the other 2 will. For row 1, I get 1 minus 2 times 0. That's still 1. 2 minus 2 times 1 is 0. And 8 minus 2 times -2 will get me 12. 14 minus 2 times -6 is 26. Now I do the same idea with row 3. I have to do row 3 minus 3 row 2. 0 minus 3 times 0, 0. 3 minus 3 times 1, 0. -5 minus 3 times -2 gets me +1. And -17 minus 3 times -6 gets me +1. Am I in reduced row echelon form now? No, but we are close. I do have a leading 1 in the bottom row, and it's further to the right. However, I still need zeros above it to be in reduced row echelon form. So I need to clear out those numbers above that leading 1. To get rid of the 12, doing row 1 minus 12 row 3 will take care of that. And to get rid of the -2, doing row 2 plus 2 row 3 will take care of that. So now let's see what we get when we perform those 2 row operations. The only row that's not changing this time is row 3. So I'm going to go ahead and fill that row in. Now my row 1 is row 1 minus 12 row 3. 1 minus 12 times 0 is 1. 0 minus 12 times 0 is 0. 12 minus 12 times 1 is 0. And 26 minus 12 times 1 is 14. Now for row 2. I'm going to add 2 times row 3 to my row 2. So 0 plus 2 times 0 is 0. 1 plus 2 times 0 is 1. Negative 2 plus 2 times 1 is 0. And negative 6 plus 2 times 1 is negative 4. Is this in reduced row echelon form now? Yes. I have a leading 1 for each row. I have zeros above and below every single leading 1. And my leading 1s are moving further to the right as I go. So now we're ready to translate this back into equations. My first equation, I have x, no y's and no z's, equals 14. My next equation, I have no x, but I have a y, no z, is negative 4. And no x, no y, but 1z equals 1. And there's my solution. It's already done for me. We get the point 14, negative 4, 1 as the solution to that system of 3 linear equations in 3 variables. So there's your brief intro into matrices. If you enjoy matrices, you might enjoy taking a course in linear algebra someday. That's all I have for you for matrices for this particular course. I hope you enjoyed the little preview into the future of math if you continue taking math. If you have any questions, feel free to drop them below. If you're a current student, you can also come to office hours or email your questions. And that's it for this pre-calculus course. I hope you enjoyed it.